Photosynthesis is the conversion of electromagnetic radiation from the sun into biochemical energy that supports nearly all life on Earth. The physiology of photosynthesis determines where your food is grown today and how locations may shift with climate change. The rest of this video segment presents a brief introduction to the secret life of plants. All photosynthetic organisms follow the same biochemical pathway. This is the Calvin-Benson cycle, or the C3 carbon fixation pathway. In higher plants, this pathway occurs in a special compartment called the chloroplast. Ribisco. Ribulose 1,5-bisphosphate carboxylase oxygenase, the enzyme that comprises up to 50% of all protein in leaves, and thereby is the most prevalent protein on the planet, facilitates the first part of this process. Ribisco exhibits conflicting tendencies in that it facilitates the combination of a 5-carbon sugar, RUBP, ribulose 1,5-bisphosphate, with either carbon dioxide or oxygen. Number 1, the reaction with carbon dioxide produces a 6-carbon compound that immediately divides into 2 molecules of 3-carbon compounds, hence the name C3 carbon fixation. 6 molecules of this compound pass through an elaborate chemical cycle that forms 1 molecule of fructose 6-phosphate, a 6-carbon sugar, and regenerates 6 molecules of RUBP. The reaction of the 5-carbon RUBP with oxygen splits it into a 3-carbon and a 2-carbon compound, and subsequently releases carbon dioxide, hence the name C2 pathway, or more commonly photorespiration. In total, photorespiration does not result in any net production of sugar. Thus, photorespiration has been viewed as a wasteful process, a vestige of the high CO2 atmospheres under which plants evolved. The balance between C3 carbon fixation and photorespiration depends on the relative amounts of carbon dioxide and oxygen entering the portion of ribisco involved in the primary chemical reactions, and the degree to which ribisco attracts carbon dioxide or oxygen. Atmospheric concentrations of carbon dioxide and oxygen are currently 0.038% and 20.946%, yielding a carbon dioxide to oxygen ratio of 0.0018. Gaseous carbon dioxide, however, is more soluble in water than oxygen, and so the carbon dioxide to oxygen ratio near the chloroplast, the part of a cell where these reactions occur, is about 0.026 at 25 degrees Celsius. Ribisco has a 50 to 100-fold greater affinity for carbon dioxide than oxygen. Altogether, because of the relative concentrations and affinities, ribisco catalyzes about 2 or 3 cycles of C3 carbon fixation for every cycle of photorespiration. Temperature influences the balance between C3 carbon fixation and photorespiration in 2 ways. The solubility of carbon dioxide in water decreases more with temperature than the solubility of oxygen, resulting in a lower carbon dioxide to oxygen ratio. In addition, the enzymatic properties of ribisco shift with temperature, stimulating the reaction with oxygen to a greater degree than the one with carbon dioxide. Higher temperatures, therefore, favor photorespiration over C3 carbon fixation, and photosynthetic conversion of light into sugars becomes less efficient. With rising atmospheric carbon dioxide concentrations and falling oxygen concentrations, the carbon dioxide to oxygen ratio at the active site of ribisco increases and thereby favors RUBP carboxylation, C3 carbon fixation, over RUBP oxidation, photorespiration. Under such conditions, plants that rely solely on C3 carbon fixation, C3 plants, enjoy higher efficiencies in converting absorbed light into sugars. Conversely, when atmospheric carbon dioxide concentrations diminished to 1/2 of current levels during past ice ages, RUBP carboxylation decreased and oxygenation increased. These conditions spawned a CO2 pumping mechanism known as C4 carbon fixation.